Okay, so maybe let's get started.
Det skulle vi nog faktiskt klara oss. Det var så lite att vi hade visat. Det var inte
Okay, so far our models are a bit boring because we just have two alleles at a single locus and a constant population size and random mating or kind of mixture, no fitness, no selection, nothing going on. So our first little complication is we're going to introduce mutants. Okay, so and then let's see what happens. If we have n to n haploids and at a very small probability there is one of them becomes a mutant, then the question is what is the chance that this mutant goes to fixation? That means the whole population becomes the same as this mutant. Okay, so do you guys have any idea? Suppose one out of the 2n guys is our mutant. What is the chance that this mutant allele becomes fixed?
Yeah, 1 over 2n.
Yeah, 1 over 2n. That's what we proved. So basically, so this result, I mean, we just proved for I over 2n. So if there's only one mutant, the probability that you, at time tau, everything becomes same as the mutant is just 1 over 2n. And this result is we're here with Kimura. So Kimura is this Japanese population geneticist, mathy guy, mathematical guy. So he did a lot of theory in the 70s and 80s. Okay. So what we saw is that so that's the probability of being fixed, reaching fixation in an all A's state. Having started I A's is simply I over 2n, which is just the proportion of A's at the start. So now when we introduce mutation, we'll do it like this. So let's suppose that mutations occur in the population whereby, say, allele A or little a becomes a mutant alpha, or say little a becomes alpha, is what not capital A or little a. So, and let's say this happens at rate mean. Then from our theorem 1, we get this result due to Kimura. So which is our theorem 2? So under the Wright-Fsher model, the rate of fixation of neutral mutations in a haploid population of size 2n is the mutation rate. So how do we prove this? So this proof is mostly just observation. So note that mutations occur to some individual in the population at rate 2n mu, right? Because each individual mutation can occur at rate mu. So for the whole population, one of them is going to mutate this way. Okay. And since this is the only individual with this mutation, so this initially was only one, it goes to fixation by theorem 1, probably 1 over 2. Okay. And so you multiply the 2, we get mu. So it's really nothing to prove, right? So we're done. So the model is now a bit more interesting, right? Mutation. What I would like to do, I'm not sure I'll have time, but at least I'll set you on this path, is so next what we'll do is we'll define something called heterozygosity and have a theorem about it, and in the construction we will define genealogies and ancestral lineages, which will lead us to defining coalescent. So now we're in 1980s population genetic theory due to Kingman. I hope to finish the coalescent.
So just one quick
question,
like
with a couple, just like so, with a couple theorems. I'll come to you in a second. Before lunch, and then we will try to get into Sage Math to do a simulation, and then let's see how time goes, and depending on that, I'll at least lay out the plan, because ideally what I wanted to do is to show the robustness of coalescent. So not just with the Wright-Fsher model, but with other models, you will actually have this limiting structure called the coalescent, and then you introduce more complications like the population size itself will change. What happens because populations are not constant, right? And the other models are Moran models, which don't have this intergenerational strict breakdown like the Wright-Fsher. Then I wanted to also introduce the simplest model for recombination, so you understand how models of recombination are built. But let's see how far we get there. We get there at all. Anyway, that's the plan. Sorry, what's your question?
So now there's only one absorbing state, right? It's alpha. Every individual will end up with alpha, right? Because
No, there will be, okay, there will be others, right? You still have little a's and capital A's, right? We're just saying that now any one of these individuals carrying capital A or little a right now has a small chance of becoming a mutant and changing their allele to alpha, which is the mutant allele. And so then we'll have three states, right? If everything becomes alpha, then it'll be fixed there. If everything is capital A, it'll still be there.
but if everything is capital A, still they can mutate, so they will end up.
Oh, sorry. Yeah, you're right. Sorry, there's no absorbing state now. But yeah, that's right. So there won't be absorbing state, but it can go to any three fixed points. That was the whole point. Yeah. So with mutations, you basically don't have absorbing states, so everything will flow. And
And in fact, most of the time, that's the only way to escape the absorbing state. Right. That's when most of these arise.
say it again. What is?
So usually mutations happen where there's one, either big A or little a is already fixed.
Yeah.
And then a mutation arises. So
Yeah. That's right. So yeah. Or you can have it arise any. You can have some I little a, I capital A's, and 2n minus. Any state you can have mutations arise. Right? Yeah. I mean, if you want, yes, to justify mutations, you say it's gone to fixation, and then there's a new mutant that comes in. All right, let's not get too hung up on this, because this model is really just to get us one started, because we really had to go to more sophisticated models, even to explain the simplest stuff, the data. So the next idea is heterozygosity. So we need this guy. So heterozygosity is defined as the probability, so different zygotes basically is the origin. The probability that two copies of the locus chosen at random without replacement at time n, or generation n, are different. So I choose two things at this locus. What is the chance that they're different? And so it's formally x to the n super 0. Okay, so it's defined like this. Xn 2n minus xn. So this is the number of capital A alleles, and this is the number of little a alleles. And then in the denominator, I have 2n times 2n minus 1 divided by 2. So this is what? This is just the binomial coefficient, right? 2n choose 2. So this tells me the number of ways of choosing any 2 out of the 2n alleles. And then this tells me the number of ways of choosing a capital A allele and a little a allele. Right? This is the ratio of the possibilities gives me the heterozygosity. Okay, so usually you bring this 2 upstairs. So this brings us to theorem 3. So let lowercase h of n be the expected value of our heterozygosity. So this is the expected heterozygosity. At discrete time n in the Wright-Fsher model. Then h of n is simply 1 minus 1 over 2n to the power of n, h is 0. Okay. So intuitively, is this making sense? So I want to know what is the expected value of heterozygosity. Heterozygosity is simply the chance that I choose the two things I choose. I happen to choose two different alleles, right? It simply comes from the frequency of finding one allele and the other. Right? So if I'm interested in the expected heterozygosity at the nth time step, right? Which means I start with some generation, and then I go back. Let's say if I take a historical point of view, I go back to the previous generation and the previous one. So I keep doing this n times, and each time I should not merge. I should not have a collision, right? So that means I have to always make sure that I pick someone, and I definitely don't pick the same guy, right? That's why the 1 minus 1 over 2n is coming, and I have to do that n times. And then after I've remained distinct for n generations, then now these two guys at the n generations in the past, they will have some expected heterozygosity, right? At that, that's what this one is. This one is the expected heterozygosity in generation 0 for them to remain distinct. So that's the intuition. But let's do the construction slowly so that we can develop the coalescent theorem from the construction for this two-allelic case. So let us label the alleles by 1, 2, because there are 2n of them, right? So let's just give them distinct labels. So it'll be 2n labeled individuals, alleles at this locus. Now, let's suppose we pick 2 individuals. At time n, labeled by x1 of 0 and x2 of 0. So let's make a picture. So I would have something like this. So these are my sort of generations, and so on. And these are my 2 choices I picked. Okay, so this is my x2. This is 0 and n are sort of pitched against each other. So x1 of 0. So these are the two random guys I picked. I picked. So there are 2n of them here, right? And time is going this way into the past. This is my present. There's one generation in the past, and so on. So here is n. So this is past. So then the idea is that when we pick this guy's ancestor and this guy's ancestor, they happen to be different. So this will be x2 of 1. This will be x. This will be x1 of 1, and so on. So we keep going back, and maybe this will be like this, and as long as we don't collide, so there's more generations here. So let's say we come back without colliding and everyone is still distinct. And so this is going to be my x1 of n, and this will be my x2 of n.
Excuse me, I'm a bit confused about what's your notion of different. Does it mean that they're different allele or that they are on a different place?
They are different individuals. So there is so basically, maybe let me do the notation first, because the picture will make sense a little bit more once I put down the definition for x's. Okay, so suppose we pick the two individuals, right, at time n. Now, each individual xi of 0 as I goes from 1 through 2n is a descendant of some individual xi of 1 at time n minus 1. You see, these are just labels. So he, she, whatever, this individual came from some other individual, and they all have canonical labels. They're all labeled, so we can talk about who is the descendant and ancestor. And then this person itself, or this individual itself, is a descendant of xi 2 at time n minus 2. And it's, so what we have now is this sequence xi of m such that 0 is less than or equal to m is less than or equal to n. This sequence of xi's gives the genealogy, okay, or ancestral lineage of this individual from time 0, right? Right individual. So that's what I'm kind of drawing the genealogy. This keeps going for first and the second randomly chosen ones for us. Okay. So now, so what we should note, if x1 of m is equal to x2 of m, so now we're just looking at these two randomly chosen guys. Say at some point they happen to be the same, that means they share a common ancestor. then x1 of L will remain the same as x2 of L for all L between greater than m and less than or equal to n. Right? That just means once you find a common ancestor, then that person's ancestor will remain its ancestor, right? So there's something called a collision event will happen.
Okay, so now you're talking about the allele will be the same in every.
No, so you should not think about alleles
yeah.
now. You should think about, yeah, I know why. So the way you want to think about it is you want to think about this, the sort of the haploid organism, because you're only looking at one locus, right? And what allele it is. Now we're actually looking at the individual itself. Okay, it has some allele, who cares? But we're really looking at just the distinct labels. So there are n of them, and because of whose ancestor basically.
And this is for haploid.
Yeah. So this is for this is for haploids, right? Or we don't have recombination, so everyone has only one parent or two. Okay, so we're getting close to early 1980s in this world, right? Yeah, so the other thing to note is if x1 of m is not equal to x2 of m, then the parental choices being independent, is the Wright-Fsher model. Everyone chooses their own parent essentially independently. We have following, we have the probability of xi of m plus 1 not equaling, so if the two guys are distinct up to time m, going backwards, they remaining distinct, at the next time step is simply 1 minus 1 over 2. So no matter what the first guy chose, the second guy should not choose what the first guy chose. That's just 1 minus 1 over 2. Okay? Right. Okay. So for x1 of n not equaling x2 of n, different parents should be chosen for all times, right? So that was the intuition that I was pointing to in the beginning. So this just means that the probability of the event x1 of n not equaling x2's ancestor at time n in all times before that. This is simply 1 minus 1 over 2n to the power of n because of the independence assumption. Okay. So finally, x1 of n and x2 of n are two random individuals from time 0, because now we're looking at what's happening at time 0. So the probability they are different, heterozygous, is simply the expectation of little h of 0 at time 0. That we don't have any control over, right? So whatever happens to be there. So we multiply that by this, and that's basically the proof. And the proof is simple, but this construction allows us to now get into something a bit more interesting, right? Because what we've seen here is a pair. So what you're seeing here is genealogies. So a pair of genealogies. Remaining distinct, right? For n generations. So now imagine you have a large population of size 2n, and you not just take 2, but you take k individuals, where k is some number much smaller than the total population size, much smaller than 2n, but it's not 2. Then the question is, what is the genealogical structure of those k individuals as you go back and find, like, what is their ancestral relationships? So that's basically what Kingman did, and so Kingman is a very famous probabilist. It's based at Oxford mostly.
You just the probability set that should it be x1 of m?
Did I say something wrong?
Or is it?
Yeah, so for all times I want them to be, yes, I think, yeah, you're right. So I think I want them to be different. Is that what you mean? Yeah. Because for them to be, see, for them to be distinct at time n, they have to be different for all times in between. Yeah, that was a mistake. Yeah, it might actually be a mistake in Rick's notes as well. So anyway, I wrote all of this.
In that case,